Hello. This is Nicholas, and I'm going to be talking about something really scary. It's called the Annihilator Method. I think I spelled that right. And also the differential operator. It's just another way of writing the derivative. So the differential operator, instead of writing the d over dx, say, of x squared, we write it as just a big D of x squared. And those are all equal to 2x. For the second derivative, instead of writing it like this, we write it like this, and those are both equal to 2. For the integral, it's, say we had the integral of x squared, we write it as d inverse of x squared, and this is suiting because the derivative and the integral are inverses, and those are both x cubed over 3 plus c. So we say that the differential operator is linear. So in other words, if I have d of x squared plus 2x, that's d of x squared plus d of 2x, which is 2x plus 2, either way. That's what we mean by linear differential operator. And so we define the linear differential operator A. We say that A annihilates, I know, scary. We say that A annihilates f of x. F is a function of x. If, when we take the operator, more assignments, when we take this operator A on f with respect to x, we get 0. So we apply some differential operator to our function f, and it annihilates it. It's gone. It's 0. It's kaput. So this method is a more formalistic approach to the method of undetermined coefficients, and it can justify our, quote, guesses for our undetermined coefficients method. I really think the best way is through an example. So let me do that for you. I don't know. Let's say we have the differential equation y triple prime minus 2y prime double prime minus 5y prime plus 6y equals e to the x plus x squared. By the way, something I think I forgot to mention in the undetermined coefficients video is that if we were doing this by undetermined coefficients instead, what we could do is we could take the homogeneous solution, so set this smojkan equal to 0, and we could then find the particular solution for e to the x. In other words, set this smojkan just equal to e to the x, and then take the particular solution for x squared. So set all this smojkan equal to x squared. Smojkan's so funny to say. Smojkan. Anyway, because 0 plus x squared plus e to the x is still x squared plus e to the x, so superposition principle says it's okay. So anyway, back to this example. We're going to do it with the Annihilator Method. My voice cracked there. So our characteristic equation is r cubed minus 2r squared minus 5r plus 6 equals 0, our characteristic equation. It looks like 1 is a root to this because 1 minus 2, negative 1 minus 5, negative 6 plus 6 is 0. So we do synthetic division. So we have 1, negative 2, negative 5, and a 6. 1, 1, negative 1, negative 1, negative 6, negative 6, and 0. So that factors into r minus 1 times r squared, not 1 squared, r squared minus r minus 6, and that's all equal to 0. So r minus 1 times, now I think that's r minus 3 times r plus 2 equals 0. And so r is equal to 1, 3, and negative 2. So this the solution to the homogeneous solution is I'm not going to write it out, c sub 1 e to the x plus c sub 2 e to the 3x plus c sub 3 e to the negative 2x. Now we want to find the annihilator. Oh, we want to find the annihilator of e to the x plus x squared. Because if we apply some differential annihilator operator to both sides, we'll just get some homogeneous differential equation here. It might be of order more than 3, like 5 or something, but it'll be equal to 0. And so what it'll really come down to is just finding roots to the characteristic equation, which is just an algebra problem. So the idea is, say, we need to, let's differentiate this e to the x plus x squared. This is f of x, call it. If we differentiate it, we get e to the x plus 2x. Differentiated again, we get e to the x plus 2. And if we can try it again and see, is just e to the x. So notice now that, see, we want to find the annihilator of e to the x plus x squared. In other words, what differential operator, when we apply it, gives us 0. Notice that f triple prime of x minus f double prime of x is, well, I'll write it out, e to the x minus e to the x minus 2, or plus 2, which is just negative 2. So if I differentiate both sides, that means I'm not going to do 4 primes. The fourth derivative of f with respect to x minus f triple prime of x is 0. And written more formally with the d notation is d to the fourth minus d cubed, and I think you would write it as of our function f, of our function f with respect to x is 0. So we can apply that operator to both sides of this differential equation, and we're gonna get a homogeneous differential equation with constant coefficients, and we know how to solve those for any order. So we apply this operator, so d to the fourth minus d cubed of y triple prime minus 2y prime minus 5y prime plus 6y. And the left side, when we apply the operator, it's going to have to be 0, right? We just showed it to be 0. So now we have to take the fourth derivative. So we get that the seventh derivative of y minus the sixth derivative of y minus 5 times the fifth derivative of y plus 6 times the fourth derivative of y. Now minus the sixth derivative of y minus 2 times the fifth derivative of y. Plus, because it's minus a minus here. Yeah, plus 2 times the fifth derivative. I always mess up on the subtraction and all that, the basic stuff. So okay, where was I? Y to the sixth derivative of y, 2 times the fifth derivative of y. Now minus, so plus 5 times the fourth derivative of y. And that's minus 6 times the third derivative of y equals 0. Whoa. So that's the only seventh derivative, sixth derivative, let's do purple, fifth derivative, fourth derivative, and then we only have one third derivative. So the seventh derivative of y minus 2 times the sixth derivative of y. Now we have minus 5 plus 2, so that's minus 3 times the fifth derivative of y. And then we have plus 6 plus 5, so it's plus 11 times the fourth derivative of y. And then minus 6 times the third derivative of y equals 0. So now this may look really bad, and I don't know what this polynomial looks like, so it might be. But notice, though, the idea behind the annihilator method is we transform a differential equation, and it only works with the same type of equations that the method of undetermined coefficients solves. You know, e's, sines, cosines, and power functions. But it takes a more formalistic approach, and truthfully, I think it's better because we don't have to do all that yucky algebra, and it forces the equation to become homogeneous, which is very nice. So the characteristic equation is r to the seventh minus 2r to the sixth minus 3r to the fifth plus 11r to the fourth minus 6r cubed equals 0. And I guess we can divide by an r cubed, so r to the fourth minus 2r cubed minus 3r squared plus 11r minus 6 equals 0. Ooh, yuck. I hope 1 is a root. Let's see. 1 minus 2, negative 1. Minus 4. Ah. Dang. Okay. I'm going to graph that on Desmos. Let's see if let me write it down real quick. I'll just write. We have 1, a negative 2, negative 3, 11, and a negative 6. And let's just see what this looks like on Desmos here. Okay. So we had an x. There we go. An x to the fourth minus 2x cubed minus 3x squared plus 11x minus 6. So let's see, are there any nice roots? Is 2.2 actually a root, or is that just... Now you could go about... I wonder if 2.2 probably isn't exactly a root. So it's got two real roots, okay? At about negative 2.2 and about 0.743. 743. Okay, I have those written down. So, and then that's two of the roots. So the other two have got to be complex. So we have a double root. We have r equals 0, right? Or that was actually a triple root. And then we have r equals approximately 2.2, approximately 0.743, and I don't want to do I don't want to do that division. See, since we have two of the roots, we can technically factor it as r minus 2.2 times r minus, or it was a negative 2.2, yeah, so r plus 2.2 times r minus 0.743 times some quadratic that I really don't want to find out, because then I'd have to divide I'd have to do synthetic division with the negative 2.2 and the 0.743, and that would just get kind of ugly. But you would get two complex roots. Let's call them a plus bi and a minus bi. Okay. So the solutions then to the differential equation, when we okay, wait. Would be C sub 1 E what was the homogeneous solution? I forget. Okay, the homogeneous solution was C sub 1 e to the x plus C sub 2 e to the 3x plus C sub 3 e to the negative 2x. And now we're going to add this particular solution, which is, so the 0, 1, that doesn't matter, plus e to the approximately 2.2x, negative 2.2x, plus e to the approximately 0.743x, and then we'd have plus, now, the complex roots a plus bi and a minus bi, that would be e to the ax times the cosine of bx plus e to the ax times the sine of bx. Whatever a and b actually happen to be. I just don't want to do synthetic division with the negative 2.2 and the 1, the negative 2, the negative 311, and the 6, and then with the negative, or with the 0.743, that's just a lot of algebra. But whatever a and b are, this this is the general solution to the differential equation. Now, that looks really ugly, and it is, but the method itself, or the idea behind the method, is pretty cool. You find an annihilator, some differential operator, when you apply it to both sides, the right-hand side of the equation becomes 0, and then the left-hand side becomes Schmajkin, but it then becomes a linear homogeneous differential equation with constant coefficients. Now, the order of that differential equation might be really high and really yucky to deal with, like mine was of order 7, but it forces it then to just becoming a problem of, well, what are the roots to my auxiliary equation, and then just, putting stuff where it fits, and then adding the particular solution with the homogeneous solution. I think it works a lot better than the undetermined coefficients, and it takes the guessing out of it, really, because with the undetermined coefficients, you were guessing a solution. Here, you are applying an